Yeah, thank you guys for coming to our session. So actually we have 2 sessions. This is the first one. The overall theme of our sessions is about armed conflicts and also the illicit economies activities, how that could influence land use. But first of all, I want to introduce myself and also the other commenters. So I'm Dr. He Ying from Kent State University in the States. And then we have Dr. Nicholas Magliocca. Please raise your hand so that people can see you. And then next to me, we have Dr. Lina Eklund from London University of Sweden. And then we have Dr. Alexander Prishchepov from University of Copenhagen. And then we have Dr. Jamon who will who will give a talk from Oregon State University. So thank you for your patience. So without any further ado, so I will pass that down to Dr. Hoek.
Just maybe we announce also special issue.
Oh, yes. My apologies. We do have one special issue, actually. We probably will send it out to all the participants. So it's a special issue that will be published in the Journal of Land Use Science, right? So yeah, we will, don't worry, we will send this message to everybody so that if you are interested in submitting your papers to this special issue, yeah, you're definitely welcome.
Hi, everybody. Thank you. I'm going to be presenting today on behalf of Corey Scher, who's not able to make it. This is work that is central to Corey's dissertation, doctoral research, which we've been working on for the last 2 years or so. We're focusing on mapping urban conflict across Ukraine using satellite radar. There we go. So you already all know this because you're at this session. Wars are disastrous for cities, communities, people, and environment. One of the things that we were able to leverage with Earth observation data is developing long-term, countrywide, geography-wide assessments of damage due to conflict or in conflict settings. And this is really filling a gap. We don't have anything like this across the world, across different kinds of conflicts, different kinds of geographies. And it's only recently that we've been able to start using these newer remote sensing systems that have been around for less than a decade to do this work really better. Oh, there we go. 1 second, there we go. This is Sentinel-1, scanning the Earth. Sentinel-1 provides nominal repeat coverage every 12 days. Globally, it's been in operation since 2015. We've got these strips day and night across all different weather conditions. Most people will say, well, what's the value of radar compared to optical? And they'll say, well, it cuts through clouds. You can see despite weather. That's true. However, Sentinel-1 radar is also extremely sensitive to changes that we just can't see in optical data. It sees the world differently than Landsat, Worldview, any optical system. One of the reasons is what's being shown here in this figure. We see the world from an oblique perspective. We see the sides of structures. In this case, it's an unobstructed view. We don't just see the roof in this image. We see what's happening not just at that point of contact, but along the side of the entire structure. So things that we just literally can't see with an overhead view, we can see with radar. A little bit of a lag here with the slide advance, so bear with me. This is not a radar image on the left, but it's something like it. We're seeing high-rise apartment buildings from the side. There's an overhead view on the right. We see minimal damage, negligible damage to the roof structure of this red polygon area, but look at the side on the left. We see burn scars, we see windows blown out, we see structural damage, we see debris. These are not visible in that overhead view. So the maps that are sort of the bread and butter, the main data source, satellite data source used by the United Nations to assess damage is missing these kinds of damage. They literally can't see it. But with radar, that's in view. And we've done a whole series of assessments in conflict settings and in other, and building on previous research that shows that there's terrific sensitivity to small-scale structural changes, even with Sentinel-1, which has a 10-meter nominal resolution. So I'm going to go through the methods very quickly. If you have any questions, let me know. Radar doesn't Of course, it works differently. We're not just taking an image. It's more analogous to a flash, like a camera flash that illuminates a room. What comes back is the structure. If you think about also another analogy we use is shouting into a room that has furniture, that has carpet, how that audio signal comes back to you, echoes back to you, that's how radar works. It's not about the color of the furniture, it's about the structures. It's about the arrangement, it's about the shadows as well that can be cast. This comes down to this laser pointer. You can't really see it here. This number of oscillations, this frequency, the wave cycles, that is the key thing we're working with here. It's the number of wave cycles. It's that distance between the satellite and whatever we're hitting, and then it's also how much randomness comes back, this sort of pure emitted signal, how much of that gets distorted, how much of that gets affected by the features that it's looking at. And when we do this over time, we can start measuring this sort of core metric of satellite interferometry, which is coherence. Coherence could be thought of like correlation, and it's similar to correlation, but it's not just the similarity, it's really the similarity in the randomness between those signals. All the things that upset that pure harmonic cycle, that's what we care about. That is, take a look at this in the equation, the trees, the topography, temporal changes over time between two images, those can cause changes. Soil moisture, deforestation, destruction, those cause changes in coherence, and that's what we can detect with satellite radar. Another way of thinking about this then, when we look over time to look at damage due to war, we look at these stable features. Buildings are very stable over time. We look at the stability, and then we track the loss of stability. We track the locations, we track the date of that really sudden and significant change in stability over time in that metric called coherence. So if it's stable, 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 to us that would look like not damage. When we see all of a sudden a different signal coming through, all these different sources of randomness of that phase cycle, that's really of interest to us. And then we can see, for example, on the right-hand side, this building, which though the roof is intact, it's completely crumbled. Overhead view looks the same. Top, from the top on the left and right, intact versus destroyed, it looks the same, but on the right, of course, we can see quite a difference. So we've been working, we actually finished this assessment in Ukraine several months ago. Everyone is aware of the scale and sort of scope and background of this conflict, so I won't get into the actual conflict history and dynamics. But suffice to say, there's been a lot of global attention to the conflict in Ukraine. We have a map there of on the upper right-hand side of sort of the distribution of acolyte events. So these are georeferenced conflict event location points. It's a little bit tough to see perhaps the scaling and pixelization, but there's a front line. You can see there, that green and blue barrier there on the right-hand side. That's the front line of conflict as it's sort of nominally reported. And we have this timeline as well, right? We can see the changes, see the temporality of the conflict on that timeline below, nominally starting in February 2022, and then of course ramping up to present day. So we're monitoring global change across Ukraine. We bring all Sentinel data, all Sentinel-1 data. We look at it in the historical period before the conflict, sort of well before the conflict. We look at the pre-conflict data to really establish those changes. And then we look, of course, at the conflict, and we do this with all available data, ascending and descending, and we look at differences therein. I'm going to skip this one in the interest of time. What we've seen, of course, is new damage mostly being detected in settlements along the front line. We have this estimate that shows that the vast majority of settlements are within, the median distribution is only 8 kilometers from where we think the front line has been reported through other sources. So this lines up where we're seeing change, it's really close to the front line, so no surprise there. But what's really interesting is when we animate this over time, this is, green is stable, it's building, urban area rather, very stable, very little change in the pre-conflict period. This is gonna loop around. But take a look at what happens as this white front line passes through this stable urban area. Here comes the front line. Very, very stable radar coherent signal, and look at this. Massive decline in coherence as the front line passes through. So these are the kind of signals that we're pulling out, and we see the result of this in different locations close to the front line. And we're capturing this across Ukraine because it's so large. It takes about a month to pull all these imagery together, but we can do these time steps locally with every single image, and then we can make monthly updates of damage across Ukraine. You'll see some damage in the far west as well. What we think is happening there is not necessarily damage. One of the things we're actively working on is trying to disentangle signs of construction, of new, say, solar panel installations, new informal internally displaced population camps, which are broadly in Western Ukraine now. All of these, of course, can change this radar signal. We don't right now have the full sort of triangulation of data to help us really disambiguate these signals. So this is an active area of research. In other words, there's some false positives that we're working on sorting out, but we think that most of that is constrained to the west. We also have we've done sensitivities with available UN data looking at their agreement from these overhead assessments using high resolution satellite data with what we're seeing. And what we're finding out is that we have very, very large agreement. So we detect well over half of all United Nations. This is a group called UNICEF that does these assessments. Very, very low false positive rate. And in areas that have severe damage, we of course see very better signals. We get higher agreement, 84% and 69% of damage in the two most heavily hit cities. But what's exciting about this is when we pair this in sort of this flow of other kinds of assessments during conflict, post-conflict, is my last slide, we're able to make an initial assessment very, very quickly, nationwide, and update it every month. And locally, we can update it every 12 days. That will tailor, will guide, follow on detailed analyses, whether it's for the field investigations, whether it's through high resolution data, whether it's through high resolution commercial radar data, which are really just coming online and have extreme value for this kind of work. So we're seeing this complementarity. What we're doing is not going to replace other approaches, but this also gives us quick estimates of unexploded ordnance, gives us estimates of rubble volume, helps us understand which areas are not really hit, safe structures, safe shelters. So the underlying core of this, right, is damage, but these are all the things that are just really 1 degree away from that. And these are some of the values that we see of this work, sharing with humanitarians and journalists as well, a lot of potential. Thank you for this incredibly fast talk on 2 years of work. Any questions? Yeah. There was a question at the back there. There's a microphone here, huh?
Thanks so much for the talk and for sharing your work. One question, you mentioned at the end, the next step is to get at these other kind of dimensions. And I was wondering, how good are those transfer functions currently to estimate things like habitability to go beyond, yeah. Thanks.
So do you mean deep learning transfer?
Or just to like go from coherence to understanding, you know, within an apartment building, how many people can still live in that building, for example, that kind of question, yeah. Thanks.
I think we're a couple years away from that, but that is definitely the direction. So one of the things we found out with this work is we have sensitivity to things like all windows, or not all, but a majority of windows being blown out of buildings. We have a couple of really nice, extremely rich case studies actually isolated. We know the detonation, we know where it happened, we know how far away that was from this building, we know how many windows have been blown out, and we can track that damage. We're actually working with a group that's repairing windows across Ukraine, and they're using these nationwide estimates of where there's damage to make the very kind of assessments you're talking about. Where should they target for field inventories, for that more detailed assessment. We can point to say, this looks like there's some serious damage, and by comparison with other things like building height data, which are increasingly available, we can start guiding those. But we really want to get to that level, as you said, of a grade of habitability. Is this useful as a sheltering structure? Humanitarians don't really care if something is totally destroyed. The UNDP cares because they need to worry about recovery, but humanitarians need to know where can people shelter safely. So that mesoscale damage, very difficult, and that's also like the sweet spot to do this work. Great question.
Jamon, I
yes,
have one
sir.
question. Thanks a lot for presentation. And we just had on Monday this discussion with the NASA Land Use Land Cover Change program. And probably you see some benefits of using data like a Sentinel-1, but where you see kind of the, not constraints, but some sort of the improvement, where you feel you miss something once you're mapping.
Great question. I'll talk more about this in my next talk that starts in 1 minute. But you'll see in Gaza, there's a lot, we see it in Ukraine too, but it's really pronounced in Gaza. Small structures, isolated structures in agricultural areas, really tough to map because we can't get the initial criterion met, which is stability. Should we even start mapping there in the first place if it's just really erratic, dynamically changing? We don't have a useful baseline. And places that have a lot of vegetation, but there may be structures there, those change erratically, and so we have to exclude those, even from our initial, valid for detection mask. That's an area of improvement that we should get with NISAR data, with L-band data, and just longer timelines as well, right? We still have a pretty short historical window working with Sentinel-1 data, and as we build it up, it should increase. So high-resolution radar 2, we won't have nationwide coverage anytime soon, but it's extremely useful for 30-centimeter resolution. We won't worry about, it's in a vegetated field, that won't be a concern so much at that level.
I had a question on the high-resolution radar. I was wondering if you've had a chance to test your methods with higher resolution imagery, how well they transfer across scales, and if you have an intuition for what value that could add having down to 30 centimeters over Sentinel-1?
We have not, because there's not a historical period for coherence that's established yet. So the leaders, ISI, Capella, Umbra, they're a couple of years away, 1 to 2 years probably, from themselves having internal coherence estimates. Backscatter is a different story. Backscatter you can do with 2 images, you can detect change, right? And people have done backscatter with high res and found it really useful. We've seen some case studies run by commercial companies just looking at natural hazard-induced disasters, say tornado that cuts through a city and levels farmhouses, levels structures. You can do a lot with that, and it's very clear. The timing, the detail, the severity. They also have different orbital views, so you can do kind of multi-look. Like ALOS Pulsar would be an older system that could do that. It's not super common in a lot of systems, but that sort of different view gives you different sensitivity to that structure as well. So that's something we can't do with Sentinel-1 and won't be able to do with NISAR either. It may be just exclusive to high-res radar.
Cool, thanks.
It's the future, but it's working alongside other systems too.
Yeah.
Okay, so let's move on to the next talk, which will also be given by Dr.
Hello again.
So you will also hear about the sound. We can continue the discussion.
Thanks. Sorry for this double billing here. Would you mind going to the Gaza, the second talk, the Gaza talk? While this is being brought up, so this, just sort of chronologically, I think it's interesting to note that while working, and it goes to a question of transfer, different kind of transfer, we had been working on this Ukraine-wide analysis for some time, and then when the Israel-Hamas war started on October 7th, we pivoted and started adapting that to monitoring that war. And what was really interesting is what we did in Ukraine does not work in Gaza. It's a different system. It's a different, the frequency of imagery and the need for more regular, rapid updates for humanitarian, basically the demand for more real-time data was different. So we had to pivot our approach. But we're going after these similar principles, persistent mapping. It's not just before, after, it's over the entire time series. This is what urban damage in Gaza looks like. So this is about 2 months into the war in Rafah City in the south. Some of the earliest damage in southern Gaza. For those of you who have followed this conflict, it's effectively a north to south, as we'll show some maps. Armed conflict impacts north to south across Gaza, but this is a sort of an outlier in that it's very far in the south, very early. We see widespread destruction, not just, again, rooftops, but buildings, lots of debris, lots of rubble. We have a rough estimate that if you take all of the rubble in Ukraine that you saw, take all that metric volume, it'd be about what you expect in Gaza, though there's a magnitude of area difference. And that war in Ukraine, of course, has been going on longer. But the scale of damage is undeniably greater than anything we've seen in the modern era. The sort of notorious levels of damage in cities, German cities like Dresden, Hamburg, or the Polish city of Warsaw, this is, at least, it's in line with those. So the worst damage that humans have ever inflicted on other humans, we're seeing it in Gaza. So I want you to watch this. This is a video that should, perhaps you could click that video. I'm sorry. Maybe this works. Hold on. There we go. I can do it here. Thank you. Look at this video. The earliest signs of damage here are in yellow. The later are in blue. What I want you to note is that I don't have any cartography here, but you can see the shape of Gaza coming through this video. In the level, the scope of damage is so great, so widespread, that it effectively outlines the region for you. Now, this work is very similar, as I said, to Ukraine, but we had to pivot to this more near real-time approach. We were making, at a time, Gaza happens to be right in between two Sentinel-1 overpasses, so we were able to get imagery of Gaza every six days, if all went to plan. Some days we would get those imagery and put out a damage map 4 hours later, 6 hours later, and share it with journalists, humanitarians. We were working at a nominal 1 map a week assessment until there were some Sentinel-1 satellite technical issues. I'm going to skip that since we already saw it. Again, Sentinel-1 works well for this sort of stuff. Take a look at this video. Now we're looking at a time series of animation. I can't get that one to go. Maybe let me see if I can. Oh, thank you if that clicked it. Thank you. Let's see if this moves. Could you try to click that map one more time? It may not be working. That's okay. This is coherence. This is pre-conflict coherence in Gaza. Not just Gaza, the region, all bright white pixels, high pre-conflict coherence. These are areas that we would have confidence in measuring our change in coherence through the conflict period. And we would see at the bottom text there, what you'll see, I'll try to get this going in case anyone does want to look at it after the presentation. We see the erosion of these bright white areas. So this animation that I was showing earlier, we see basically the eating away of high coherence areas which were building, which were infrastructure, buildings. Every school in Gaza has been damaged. Every hospital has been damaged. Right now there's 2 in operation. Estimates of 70% of all residential buildings have been damaged or destroyed. It's widespread, systematic, total war. When we see this progression from our very first damage map on the left to the damage map on the right, one thing you may note is that the labels for the governorates, North Gaza, Gaza, etc., we had to kick those out of the map because there was so much damage that the labels were occluding the detection of that damage. That was not expected when we started this. We had to change literally how we make a map because the damage was so severe, the red areas, it was overtaking the rest of the image. This is already last April, but we've stayed more or less, with the exception of Rafah, at about these levels. You can see 70%, 74.2% of buildings across Gaza across North Gaza and Gaza. Overall, we're approaching 57%. It hasn't changed that much. Actually, it's 59% is our estimate across Gaza. Here's the timeline. Large jumps in here correlate extremely well with known Israel military operations in the area. Extremely fast rate of damage in North Gaza and Gaza, coming away from this slower, more progressive damage in Rafah in the south. We're at 59%, as I said. That aligns very well with the United Nations estimate of 66% and the World Bank, which has a similar estimate of 62% residential. Suffice it to say, 60 to 66% is a reasonable range of likely damage or destruction of built-up areas across, buildings across Gaza. Now, we do much better at capturing what the UN estimates across Gaza. 99% of all UN estimates, of which there are only 6 that have been made, six maps that have been made, we capture 99% of those right off the bat. Automated, 4 to 6 hours, we can capture 99%. These estimates take 2 to 4 weeks to make for the UN, so we can generate these much, much more quickly. And you can see very similar patterns of damage. However, what the map on the right is showing is point locations that we've sort of scaled up to sort of look like a pixel, but these are point locations that the UN points, not pixels. Sasha asked this question, what are some of the limitations? Well, we know small clusters of structures in agricultural and rural areas, we tend to miss those. Partially a spatial resolution issue, partially a coherent stability challenge. So you can see the blue patches there. Those are spots that we miss, that UNOSAT has confirmed at least rooftop visible damage or destruction. But again, by and large, very, very high agreement. Some notable examples of lateral damage, those 3 high-rises, this is a picture taken by the Israeli military, those 3 high-rise buildings in the back, you can see windows blown out, burn scars, those are damaged. We see tons of, many examples of lateral damage due to the use of these large-scale bombs that that have a blast radius of up to 90 meters. This is just showing the 31 meter, where the outermost diameter here, showing where fatalities, total destruction of buildings, but the outermost extent of this kind of particular bomb goes up to 90 meters. That's a big catchment, right? That means that where one of these craters that you can see in aerial imagery in which different journalist outputs have mapped, all the buildings surrounding that up to 90 meters may have been impacted. So these 3 buildings, though UNOSAT doesn't detect them, we catch them in radar imagery. We see that lateral damage, which is plain to the eye. It's also plain to radar, but these are 3 notable examples missed by the United Nations approach, which is overhead, just as sort of a pictorial example. Lots of other areas where we're actively investigating disagreement and agreement, the reasons why we have agreement, the reasons why we have disagreement. It is not just a function of severity of damage. It's not just severity. A small structure that is totally destroyed may give you a similar signal as a larger structure that has moderate damage, but over a larger area, right? So there's a trade-off. Not a trade-off, there's sort of a combination of impacts or of conditions that can result in the same kind of signal. So it's not just a severity difference, it's the urban morphology, it's the size, it's the kind of damage. Is it cosmetic? Is it textural? Is there actual volume that's been displaced, et cetera? All those things are contributing to these disagreements. And we've been in good touch with the United Nations over the years, trying to figure out some of the reasons why we may be getting different results. So this work, as I said, we're producing these maps very rapidly, sharing them with journalist agencies, sharing them with humanitarians. There's been broad-scale uptake and response to this effort. So far, we have over 320 news articles citing these data, reporting on the statistics, several UN reports across 14 countries that have been using these kind of statistics. One of the things I'd like to close on that I think is so powerful about this, that we haven't perhaps had the opportunity to see in previous armed conflict settings when satellite imagery have been used is the value of transparency. Now, I would never argue about the objectivity of satellite remote sensing. These are not objective assessments. And these are certainly, there's politics surrounding this, there's ethics, there's subjectivities that abound, but they should be methodologically transparent. And these are open data. So anyone here can use the same data we have and should, with the same parameterization, get the same results. And they could improve it, they can adjust it however they like. That's incredibly useful to have that scientific attribute brought to the fore of discussions of the effect, the impact of armed conflict on communities and landscapes. Now, that's one thing that I think coming out of this conflict, when it does end, formally end, and other conflicts as well, that is sort of an untapped potential to date, is finding common ground, not on why the war started, what we should do next, but just what happened. What happened to Gaza? What happened to Ukraine? What is happening in Gaza? What is happening in Ukraine? What is happening in Ethiopia? What is happening in Sudan? There's a terrific amount of transparency that hasn't really been brought up by policymakers, by local governments, but we see examples of this. On the map on the left, that's a left-leaning Israeli newspaper Haaretz. The image on the right is from a more right-leaning Israeli news channel, Channel 12. They're using the same data, talking about the same things. Interpretation may be different. The takeaway narrative may be different, but it's the same map, it's the same statistics. So we have some semblance of agreement on what is actually happening. Thanks very much. Any questions?
Any questions?
Yes.
What is your intake? What is your approach in this story? Where would you feel you would like him to step out and let it go?
It's a great question. So Sasha was asking about neutrality as a scientist. There's a couple of answers that I would have, or parts of an answer. One is that we map wherever we can and we've been asked to, or we think we should. So we are now mapping in Lebanon. We're also mapping in northern Israel. Northern Israeli communities have been hit by rocket fire. Lebanese communities have been hit by rocket fire. So we're mapping both. We're not taking a side. We're mapping both sides of the border, in that sense, right? So we're not just thinking about one side of the conflict where we're mapping. The other facet of that is just understanding the limitations of what we know about the conflict and what we can comment on. So we can talk about our analysis, we can talk about these statistics, but questions of, is this legal? Is it proportionate? Is this war justified? I mean, people ask, these are sort of obvious following questions to ask, but we have no comment on those, right? We're not qualified to talk about that. So we can talk about our analysis and talk about the limitations of the analysis and how that might have implications for follow-on assessments. But we really try to scope how we engage with this just in places that we can actually confidently talk about. So yeah, constrained engagement.
Thank you for the talk. I wanted to go back to what you said about the difficulty of mapping in vegetated areas.
Yeah.
Is it not possible to get a coherence from the vegetation signal itself, like over time, and then from there, if a structure was there and it disappears or it's damaged, the coherence should change, no?
That is possible, and we would like to go in that direction of better understanding the environmental drivers of coherence variability, as with regard to identifying structural change within that vegetated mosaic. We're not there yet, but the main issue with doing that is we make an assumption, we have a criteria and a requirement of stability before the conflict to even start mapping something, and if it's so variable already, we have to throw it out. But if we can model it, then we could start accounting for that better, and that's the direction, the source of coherence variation from vegetation, then we could better account for that. And right now we can't account for it, so we mask it out.
Okay. Just a follow-up. Could it, if using optical data, then would, in combination, wouldn't that be a bit more helpful?
It would, but high-resolution imagery is not available over Gaza, broadly speaking, and at the time steps that we're interested in. And Sentinel-2 imagery or something like that is not necessarily going to give us the same kind of indicators of variation that are structural that we're concerned with. The optical data would tell us about the chlorophyll content, but not other things that we're interested in.
You get the built-up.
Sorry?
You can map built-up area from optical data.
Sure, you could detect built-up area, yeah.
Cool.
Yeah. There's been, I would say, please correct me if I'm wrong from anyone else in the room, I would say limited effectiveness with open optical data for detecting urban damage. There were a couple of papers on Syria, and it was unfulfilling, the results. So there's structural, that's done with some, at the time, with some simple textural pattern analyses, so there could be different approaches, but what we've seen with the sensitivity to structural change of radar is well beyond what we can detect with optical, so it seems uniquely helpful, but there's certainly information in optical to be brought in, we just haven't brought it in yet. Sure.
Thanks, Jamon. A way you phrased something there caught my attention of saying, you know, we map where we're allowed to map. And I wonder if you could talk a little bit about what that process looks like. What does it mean to be allowed to map somewhere, and what does it look like when you're not allowed to?
I'm not sure what I meant if I said aloud,
okay.
But I think I did say we map where we're asked to,
okay.
and where certainly there is a question where we can with the data, but there are some restrictions on mapping in active conflict settings. So when we share data with humanitarians and journalists, we have gotten feedback that we're detecting change in military bases, in sensitive spaces, and so those are removed from their reporting. We don't actually know where they're talking about, so we're sort of left out of that equation, but there is another masking that happens with the sort of public dissemination, cross-referencing of data through news reports and humanitarians. But I mean, the bigger issue in terms of access is this embargo on commercial satellite data. It's been extremely worrisome in Gaza and other conflict settings. There's also effective embargoes, effective unavailability. There's no Sentinel-1 time series over Khartoum, Sudan, for example. There's no data that are available to do this kind of analysis. So we're just limited in applying this inherently due to the lack of coverage in certain spaces. And that's goes to show, golden age of Earth observation data, yes. Lots of gaps, lots of challenges, lots of limitations still.
All right. Thank you, Jamon.
Thanks.
So now let's move on to Dr. Lina Eklund from Lina University in Sweden.
All right. Okay. Thank you, Hoek. And thanks everyone for being here. I'm Lina, and I will talk a little bit about whether Rojava is greening. So, all right. So I'm the one who's here, but I actually have a whole team behind me. We are an interdisciplinary team with people from political science, human geography, another physical geographer like myself, and also someone from disaster risk management. So we are constantly having really interesting discussions about how to interpret our results. And this project called EcoSyria has one question that is engaged with conflict environment nexus in the region. So when I say Rojava, how many here know what I'm talking about really? Like a few of you. Great. So for those of you who might not have a clue, Rojava is the Kurdish name for the region in Syria. It means west, So it's the western part of the whole Kurdistan region that covers several different countries. And Rojava is the Syrian part of Kurdistan. And Rojava is interesting because it has a certain, certain development since 2012, where the Kurdish forces took over this and started controlling this part of Syria in the north and northeast after the start of the Syrian civil war. So there is a model or a movement talking about making Rojava green again. It has 3 pillars. One is direct democracy, gender equality, and then ecological sustainability. And this is quite an interesting thing in this particular region, and also considering that this is happening in the middle of a war zone, in a war that has been going on for over a decade. So, yeah, let's see. So this is Syria, and the Rojava area, or the administration of North and East Syria, is located in the black, within the black areas here. Let's see if I can point at all. No. So you see the arrows from the point there, autonomous administration, which is the governing entity of Rojava. We also have some areas that are interesting, which is Afrin, which was occupied by Turkey and the Syrian National Army in 2018. We have another region between Afrin and the AANES area, which is called Operation Euphrates Shield. It's also occupied by Turkey as NA since 2016. And then we have Operation Peace Spring, the long strip in the north, which was occupied in 2019. So these areas are in different ways claimed by the Rojava, but they are currently not being controlled by the AANES. I also mentioned the NES, which is just the general description of the North and East Syria. So as you can see, there are lots of different ways to talk about this region. And we are in the early phases of this project. So we are asking a somewhat simple, maybe stupid question: is Rojava greening? So that's the first thing we wanted to find out. We use quite simple methods. We look at NDVI trends, we look at land use land cover analysis, or changes in land use land cover, and we also do a visual interpretation. I can also add that we're currently collecting survey data in Syria, but I don't have any results from that yet. All right. So this is the resulting maps of the NDVI trend mapping. So we look at 2 different periods. We have 2003 until 2012, and then 2013 until 2022 to try to capture this before Rojava and after the new government gained control of this area. And it's kind of hard to see what's going on, and maybe especially hard with this screen. But I want to bring your attention to this part here. So in the early period, we see that the annual mean NDVI trend has some areas that have a negative trend in the dry areas, in the, well, maybe central parts of the region. If you look at the next, in the next period, the later period, these areas have disappeared, and there are maybe even a few pixels with a positive NDVI trend. If we look at this, the maps to the right, this is the interpercentile range, which is basically a more sophisticated amplitude, minimum value compared to maximum value over the year. And here we see another kind of, well, maybe similar pattern in the early period. You have a brown, like, this is not a browning trend, but the amplitude is decreasing during this period. In the second period, we see that we don't really have this decrease in the same area, but it has shifted upwards towards the more fertile areas. So here in the further south, it's maybe more marginal lands that are not cultivated each year. In the north, bordering Turkey here, this is where you have a lot of like very high intensity cultivation. Right. So I also gathered some land use or land cover data, it's based on a data set that we have developed for Syria and Iraq, particularly. So we look at how the levels of cropland and other types of vegetation fluctuate throughout the years. And we see for the AANES area in the upper left, let's see. Well, the first thing is that we see a decrease in this double cropping cropland, especially since 2012 and onwards. Then we also, we see this interesting peak in 2019 where cropland area really expands from what's normally like 20 to 40%, or even less, 20 to 30%, and then goes up to over 60%. So what happened there? And then 2 years later, it goes back down again, back to normal. So we're really curious about what happened, and I will talk a little bit about it in the next slide, but I also want to bring your attention to Afrin, which is a slightly different area. It has a lot of tree cover, a lot of orchards, a lot of olive trees. And this is the area that was occupied by Turkey and the Syrian National Army in 2018. And as you can see, the chart looks quite different. There's more green. There's this other vegetation class that we have, which is, I mean, I'm not super proud of it because it's not very detailed, but it is useful to say something about what's going on. And what has happened in this area since 2018 is actually, there's a lot of news reports about destruction of olive trees and illegal logging in the area. And we can, let's see if I have, come on. There we go. So I just wanted to show you here that since 2018 or 2019, we actually see a decrease in this other vegetation cover. All right. So just briefly on the 2019 anomaly, which we think is quite interesting. What happened there? And we actually see widespread cropland expansion in both Syria and Iraq. So this is not specific for Rojava, it's not specific for Syria, but it's also happening in Iraq. It's not happening so much in Turkey, as far as we can see. And these are areas that haven't been cultivated since before 2000. We can see that they look like cropland areas, but they are not cultivated in our data set until 2019. We have some possible explanations. The first one is concerning water. It was a really wet season in 2018 and 2019, but that doesn't explain it all. You know, you still have to sow and manage the land. Then we read that the FAO and ICARDA had a project for producing seeds to generate incomes. That was also in 2018 and may have been part of causing this, this big increase. And then we also have labor. I mean, you need people to work the land. And we read that there has been a return of IDPs to certain areas of Syria. We don't have the exact locations, but it's something that we will continue looking into. There are some unknowns, and one of them being land tenure, like how do you get access to land in Syria, and how do you get access to land during armed conflict? Like, is there a difference, perhaps? Also wondering about farmer decision making. How do you know if it's like a good year is coming up so that you decide to cultivate areas that have been fallow for almost 20 years or maybe more? And then we're really wondering, why is this happening not just in Syria but also in Iraq? Right, and these images show, I mean, it looks better on my computer screen, but you can see that in April 2019, it was very red, it had a high near-infrared reflectance, and just a few weeks after that, the reflectance was lower, so it means this area has been harvested, so it's not just weeds because of a lot of rain. And then I have a lot of small images that I will skip. Yeah, so these are my conclusions. I mean, the question is Rojava greening is, again, it's a bit stupid. But we see maybe some signs of greening, some signs of decreasing browning. We see less double cropping, which could be a shift in agricultural system, like how you manage the land. It could be a more sustainable approach with less intensive agriculture, but it could also be the effects of armed conflict. It's hard to know. Yeah, we have a reduction in non-cropland vegetation in Afrin. We can't know if it's because of armed conflict, but we will look into it more. And then this expansion of cropland is just really, really interesting. So, yeah, we can ask another question, which is what does greening really mean in this context, and how do we understand it? Thank you very much.
Yeah, so we also saw the massive expansion. Oh, sorry. Yeah, it's quite interesting because we also saw that in the growing season of 2019, there was a really strong increase in agriculture activities, and associated also with the fire. Some other scholars mapped the fire. They also observed a lot of fire in the year of 2019. Yeah, one was in the field talking with the Syrian refugee farmers, and I didn't get a clear answer, but it's quite interesting. I heard that from many farmers that they just sow their land regardless whether there rain or not. In some regions, maybe they get one harvest out of 5 or 6 years. And then in 2019, it happened to be really rainy. So I wonder if that's reason that farmers they sowed and then it happened just to have a lot of rain. So then there's a sudden increase of the agriculture. I know that you mentioned in your slides, but I somehow also want to validate that. Yeah.
Well, thanks. That's that's really nice to hear that you have asked about this. And yeah, if it is that the people sow every year, then I guess that would make sense. Thank you.
Thank you so much for your talk, Lina. I really enjoyed hearing it. One thought that I guess came to me while I was listening about the Turkish incursions in Afrin and elsewhere. Do you have, or have you explored at all whether access to different markets or access to the energy infrastructure in Turkey has expanded in these areas during this period? And is that maybe contributing to some of the trends in the non-agriculture vegetation? It's just something that could be interesting to see whether it's the areas are being more integrated into the Turkish state, even though maybe it's not de jure part of Turkey.
Thank you. Yeah, I think this is one of the ideas we have, and that's why we're including these areas that are not currently controlled by the ANES, that we can see them as like, maybe there are no control areas, but there are areas where you have different governance and different things going on, so we can see and compare them, and yeah. So this is something we should look into, and we'll hopefully look into. Thank you.
I had a question about the drop after 2019. To some extent, I suppose if there was a clear answer on why there was an increase, maybe it would be possible to understand. But do you have any ideas why there was a sudden drop straight after?
I think, this is about water availability. So in 2018, 2019, there was a lot of water, a lot of rain. And I think the 2019-2020 season was also a bit above average, if I remember correctly. But then it went back to normal, or maybe even below normal. So I think this would be, the main explanation. But there might be other reasons as well. It's a good point. Thank you. Thank you.
Over to you.
Yes. All right.
So next speaker is me. So could you please pull up your slides? Yeah. So first of all, thank you for coming to our session. And it's quite interesting, early this morning at the plenary discussions, we heard a few keywords, right? We heard about the conflicts. We heard about the remote sensing, and there are some discussions about what we can do using satellite data. So today's my talk is mainly focused on applications of using remote sensing technique to understand the impacts of the war. Okay, so I think I'm going to skip this slide because I think there's a lot of talks about our satellite data, but also echo what the question discussions earlier with Jamon, the objectivity, because it's really hard to gather information for any conflicted areas. And probably the satellite data is the only available information you can collect. And also it's very important, and also earlier the discussions with the baseline, how we could compare, what is the baseline, what is the pre-war status, so that we can compare the current imagery and with the imagery collected before the war in order to infer the damages. Okay, so from here, I'm going to switch the gear a little bit and just to use two case studies. The first one is the war in the Caucasus, and the second one is the ongoing Israel-Hamas war. So the Caucasus is really a fascinating place. I've been there, and I was really amazed by the diversity of the ecosystems and also the cultures. So it used to be one country, Soviet Union, but unfortunately after collapse of Soviet Union, and this region became quickly a battleground. So if you see in Northern Caucasus, noted in the orange dots, they indicate the individual conflict events that is occurred during the Chechen War. Actually, it is the Chechen War that Putin came into power because Putin was really successful there. So the question here is, what happened in the past, and second, how we could link remote sensing observed changes into the war. As we all know that, if we directly see the changes in the satellite data, it doesn't mean that it is only caused by the war. And unfortunately, we got a grant to study this, and the PI, Dr. Volker Radulov, is sitting in the back. Okay, so let's dive into remote sensing technique. So the class, or the trend of interest here is agricultural land abandonment. So why we look into this? Because we know that in any conflicted societies, the food security is one of the biggest concerns. And that's why, for example, agriculture has really meaningful, can deliver, the information that can be used for humanitarian aid and also can be used to guide the post-war reconstructions. But when we started this project, I was really amazed that there was no reliable approaches, remote sensing approaches to monitor agricultural land abandonment. So our first step is to come up with new methods, remote sensing methods that are unable, to reliably identify agricultural land abandonment, and also the following process, for example, whether there's a recultivation or not. So I'm going to skip the technical detail, but happy to answer any questions afterwards. So this approach is really this approach is novel, but also it is very important for us in order to understand the impacts of the war, because we need to know the timing, if there was abandonment, when that occurred. So that's why we are able to generate maps like this, different colors indicates the timing of abandonment, because the time is essential if we want to understand the impacts of the war. However, we cannot draw the conclusion. If you look at this figure, the different dots, different size of dots indicate individual conflict events, and they seem like they really align well with the abandonment pattern we observed. But we cannot draw the conclusion because we know that agriculture abandonment is really common in the Soviet Union areas. So just because we have a pattern like this, we cannot say that the wars caused the abandonment we observed. So what should we do? Then we came up with using the econometric models to understand the relationship of the war and also the observed abandonment and also recultivation. So again, I will skip the technical details, but the purpose here is we want to rule out the other factors, like a climate, like a soil quality, so that we can fully focus on the soil impacts of the war. So we use a bunch of econometric models, and we found that indeed the wars caused agricultural land abandonment. And also, it's not just the location, like how close the war is to a farm, but also intensity matters. The intensity here means the number of the conflict events and also fatalities. And also, we also found a land use legacy here. Even after many years, the places that are closer to conflicts have a few recultivations. Okay, job done for the Caucasus. However, we look at the Caucasus in, how to say that, retrospectively, a respective view. That is happened, long time ago, 20 years ago, 30 years ago, then we look at it back. But for some armed conflicts, like Israel and Hamas war, it's more urgent. We cannot wait 20 or 30 years later and to look into the damages. And Israel-Hamas war is like, as Jamon already talked, it progresses really fast. Almost daily you hear some news from the media outlet, somewhere got bombarded and people killed, etc. So the challenge here is how we could reliably and also to provide a near real-time estimate of the war, the damages of the war to measure it. But we face a lot of challenges here. When I started working on this, I thought, okay, just a piece of cake. I have done a lot in the past, but apparently I underestimated the challenges of using satellite data to monitor the agricultural land in Gaza. So here you see, we can see the field in the US, in the States, really typical farm in the Midwest. And then here you look into Gaza. You see a lot of stuff, they are same scale. We can see like individual trees, you see the green dots there, and also we see greenhouses, all sorts of stuff. And then when I started this project, I tried to use the existing publicly available data like a Landsat. Okay, so, but first, maybe let's clarify the research questions here. So we mainly focus on the agricultural land. Here, because as we know, food security really matters here. And then the main challenge here is how we could assess the damages in near real time. And here we mainly focus on two agricultural land use. The first one is the tree crops, like olives and the fruits, and the second one is the greenhouses. Why do we look into them? Because these two classes are the most important agricultural land use in Gaza. And they're very different, right? If you look at greenhouses, it's just like a man-made buildings, whatsoever, and we look at olive trees, for example, they just look like forest. So that's why they pose additional challenges in remote sensing work. And now let's look at satellite data. So what do we have here? So here we're looking at is Landsat data, 30-meter resolution, right? We cannot really see much. It's just all blurred. Now let's look at Sentinel-2 data. 10-meter resolution. Okay, 9 times better than Landsat. Great, we can see some features there, some structures, but still it's really difficult. And then now let's look at the planet scope data from Planet Labs, a commercial company. It's a 3-meter, which is much, much better. We can see the patterns much clearer. And then let's look at the very high resolution data, the sub-meter planet SkySat, 50 centimeter. Then we can see pretty much everything. So I started with Sentinel-2 data actually, but I found that it didn't really work well. So eventually I decided to use the 3-meter and also 50 centimeter Planet Labs and also Planet SkySat and Planet Scope data. So here I borrowed one of the models I have developed in the past, actually, which is for grassland monitoring. So that method is initially designed to capture the mowing events in grassland. So if there's like a mowing event, then that's a drastic drop in the time series. So I applied this approach to monitor the tree crops damages. So here the profile, you see they are fitted for one just single planet scope pixel. And we see a lot of noises here because mainly the noises, so the figure on the up left, it is, you see the drops, that's mainly because of the noises. That's why it's important that, we use a harmonic model in order to rule out the impacts of the noises. And then once we have this model built, then we can predict the future. And then we can compare what we observed with the prediction to infer the damages. Okay, so what do we got here? Next slide, please. Yes. So here is one animation, just shows you the damages of the tree crops across Gaza, across the space and the time. We see that quickly it's just expanding, but first it started in the north. This is where the war just started, and then it quickly spread out into the south. And if we compare what it was October 1st with the end of the June, the later June, we see like a lot of damages. However, can we see that more than 80% of the land they got damaged just because of remote sensing analysis? We cannot, because all the maps have errors. So that's why in the following work we used more than 1,000 examples in order to contrast the error-adjusted area estimate. So this is what we got. So by the end of September, we found more than 60% of the Gaza's tree crops were likely damaged. And definitely we see some, dynamics there, but a lot of damages that occurred before June. And if we look at different, governor reds, we saw that a lot of damages that occurred in the north. And in the region in the south, like Rafah, if you follow the news, and this is the places where the conflict is ongoing, we see an increasing trend in the damages. Okay, how about the greenhouses? Greenhouses is a different story because it's very different. It's not like trees, not like any other crops. So here we use a deep learning approach, actually some model from Meta AI. So we use this model because it's already pre-trained on millions, if not billions of imagery, so it's really robust. So we were able to reliably identify individual greenhouses. We identified more than 7,000 individual greenhouses. And then use a regression model, we were able to also identify the damages to greenhouses. And here we see a very similar pattern to the tree crops damage, but still a little bit different. But what is the most devastating is we found that in Gaza City and North Gaza, the two governor reds, every single greenhouse was damaged. There's nothing in contact. Okay, so this work, got a lot of media exposure, but also it's very enlightening to me because when I spoke with the journalists, I also get their perspective. So which is really important in order to understand what happened in Gaza. And also our work has been used by UNEP, for example, in their damage estimate, which is really important because we needed to also focus on the post-conflict recovery and reconstruction. And our work provided a baseline about where should be invested. Okay, some quick take-home message, and we found that remote sensing perhaps is the best way to monitor the impacts of the war. But however, remote sensing shouldn't be the only one, as we learned from the Caucasus work. In order to build a causal inference, and we need also the other models in order to build the connections. And we also, yes, even though we have a lot of methods actually, existing in remote sensing community about how to monitor the disturbances to ecosystems, but many models, they cannot be directly applied to monitor the damages of the war because the wars are indeed very unique. We are talking about human decisions. We're not talking about hurricanes. We're not talking about flooding. So that's why it's really complicated and very dynamic. And this field is still evolving, how we could develop a new and a novel remote sensing algorithm to reliably monitor the near real-time damages. Thank you. I forgot to say that. It's not a one-man job. I have a lot of collaborators, and also thanks to the donors, the funding agency, NASA, to support our work. Questions? Okay, if there's no questions, we can move on to next. Okay, Shasha.
Okay, that's working. Thanks a lot for presentation, and we again see that different scale of the conflict would require maybe different also levels of working with the satellite data, and what I see that you also work intensively with the PlanetScope data in the case of a conflict. And then you also highlighted about importance to account not only for remote sensing data, yet we often see direct implications of the conflict, let's say like in the case of Gaza, but the same applies maybe with the discussion with the Jamon. But can we also witness and see some leakage effects, spillover effects also, maybe with the aid of the satellite data, but also bringing this kind of the land system context to see implications also to elsewhere, besides of just looking directly at the location?
Yeah.
Thank you.
Yeah, so I think your question is towards the indirect impacts, right? Or
it's a really good open question if it's a direct or indirect, but it may be both. Thanks.
Yeah, that's a really good question, because what I show you just showed that they are like a direct impacts, right? But actually, if we take the indirect impact into account, then the damage rate is much higher. For example, what I didn't show is a lot of fields, a lot of farms in Gaza, they are not, damaged, but you can predict that they're going to fail because there's no irrigation anymore. The farmers cannot attend to their land. So even though the farms they're still there, they're not got damaged, but they will not survive without water, without management, etc. So this kind of indirect impact, it's really hard to measure from satellite data because a lot of things going on. There's a lot of regional contests and different regions. They have different land use histories and different management schemes. We're talking about, even though we are looking at satellite data, we're looking at pixels, but actually we're looking at all human decisions. And human, us, are the most complicated creatures, probably. So that's why, it's really fascinating. That's why we need to bring more, information, interviews, surveys, and so forth, regional contests, in order to better understand what we observed from satellite data, and also to be aware what we cannot observe from the satellite data.
Okay. Thank you so much for your talk, Ha. I guess 2 quick questions. The first is, you mentioned the trees, the tree crops being damaged, and you had the binary map there of damaged and not. I was wondering if you have various thresholds of damage, like are the trees being bulldozed or completely burned, or if maybe just some branches or some of the vegetation is getting disturbed by a bomb explosion. And I guess the second question, just from what you were saying now, I know in Gaza there's some areas that 20, 30 years ago they weren't cultivated at all, and like you said, irrigation has been brought in. I'm wondering if you're looking at how soil moisture is changing, or other kind of maybe measures that would look at those drivers of degradation.
Yeah, a really good question. So the first one actually is the Gaza is really special. If you look at satellite data, especially the very high resolution data, you pretty much just see everything's gone. It's not like forest degradation, right? You have some trees there, some trees died, you have a few trees within a field, but in Gaza, it's everything completely wiped out. So there's pretty much no threshold here because it's pretty just trees and bare soil. So it's really unfortunate, but it made my remote sensing work easier actually, so I don't have to look into different thresholds. And the second question is about the irrigation, is that right? It's about the, sorry, I think I missed your question, the second one.
So are you looking at any measures of irrigation or soil?
Yeah, that'd be fantastic, because if we think about a post-conflict reconstruction, we want to know the soil, right? We want to have soil information, whether the soil just lost their productivity forever or not. So this is also a limitation with using remote sensing data. We have some data to monitor the soil moisture, of course, but still, when we go to this kind of really small fields and really dynamic environment, it's still quite challenging. Thank you. I think I should stop here. All right, so last but not least, we have Chris to present his work. Thank you.
Thank you very much.
I have the clicker.
Sorry. Jeez. Hello, everyone. I realize it's getting close to lunch, so I'll try and speed through this. So I'm Chris, I'm a PhD student from the University of Edinburgh, and I'll be presenting some of my work, which is entitled Resilience, Remoteness and War Shape the Land Cover Dynamics of one of the largest Miombo woodlands. So thank you to my co-authors there. Louisa is here, and also thank you to my funders. So my study area, as you can see outlined in red on the map, is the highlands of southeast Angola. Yeah, there's a bit of a lag. It's the headwaters of the Okavango Delta, and one of the largest blocks of woodland in the Miombo ecoregion, and the largest block of woodland in Angola. Now, it largely consists of Cryptocephalum dry forest, but also Miombo woodland, which is a type of wooded savanna. And it was the center of conflict in the Civil War. This area was kind of a stronghold of UNITA, which were the faction that controlled a lot of rural areas, and they were fighting against the MPLA, who would then go on to win the war in 2002, who now rule the country. And you can see on the map the roads network in orange, which doesn't really penetrate into that area of woodland. And since the end of the war in 2002, there's been little infrastructural development. Partly, we think, probably because of the marginalization of communities there and their association with UNITA. And because of this remoteness, due to this lack of infrastructural development, this region has seen recent interest from conservationists. And I should just say the framing of this work is that my chapter that covers this work was initially looking at kind of land cover dynamics to help inform conservation interventions, but we found that there was really interesting findings relating to the war, so that's what I'm presenting today. So my research questions then were, what was the effect of the conclusion of the Angolan Civil War on the woodlands? What were the temporal patterns of change? And then, sorry about this. What were the causes and drivers of land cover change across the landscape? And we know that conflict can have diverse outcomes for land systems and biodiversity and livelihoods. So my methods then were I created a land cover time series from 1990 to 2020 using the Landsat archive, and then we used a hidden Markov model to harmonize the time series and suppress spurious changes such as urban pixels transitioning to dense woodland within a year. From that time series, we extracted change maps for deforestation, so that's deforestation to cropland, canopy opening, canopy closure, and secondary vegetation growth from cropland. Just to note, here I'm using the term canopy opening and not woodland degradation, because in these savanna systems, an opening of the canopy doesn't necessarily equate to ecosystem degradation. And then to assess the kind of correlates and drivers of change, I used those change maps as kind of a response variable, and then a number of other layers as predictor variables, so population density, distance to roads, distance to markets, distance to urban, etc. And so here's my time series animated from 1990 to 2020. A few things to point out. We see this advance in cropland in the northwest of the region. This is the most populated area of the whole region. In this sort of core extent of woodland, we see transitions between dense woodland and forest to more open structures of woodland. And then in the south, this is a much more arid region with higher fire activity. We see transitions of woodland to more open savanna. And so then the main findings relating to the war were that we saw a peak in canopy opening towards the end of the Civil War. And then almost a decade later, we found that there was a peak in canopy closure. Now, we associate this peak in canopy opening with the resettlement of displaced people towards the end of the Civil War. And this signifies a short-term positive outcome for the livelihoods and well-being of those displaced people, but a short-term negative outcome for biodiversity and carbon. So that peak later on, that in canopy closure, almost a decade later, that's kind of a legacy effect of the Civil War. We found that canopy closure offset almost 2/3 of all canopy opening. And this, we think, is due to the remoteness that the war facilitated, the destruction of infrastructure, roads, bridges, contamination of the land with landmines, which disincentivizes land use and sort of disincentivizes access to that whole region, really. So this condition of remoteness, but also the condition of resilience of these Miombo systems and their ability to recover post-disturbance. We didn't see an exponential rise in deforestation across the whole area, but there certainly was around urban areas. And there was no significant change in total woodland cover, but there were changes in kind of woodland structure. So when we look at spatial patterns of change, this is around Manong in the southwest of the region, we see what we might expect from spatial patterns of land cover change around cities in the Miombo ecoregion. So we see deforestation closer to urban centres, canopy opening further out from that, and canopy closure in more remote areas. And we found, this is a partial dependence plot from our random forest model, we found that urban centres had a big impact on deforestation, where deforestation was most probable, closer to urban centres. In Angola, over the wartime periods, there were over 4 million internally displaced people, the majority of which relocated to urban settings, living with host families and taking up work in informal jobs, such as collecting tree harvesting and collecting timber for buildings and for wood fuel as well. And also, in just 3 decades, Angola went from a majority rural population to 60% of people living in urban settings. So the war sort of acted as a catalyst for this rural to urban migration, which is fueling this urban demand for agricultural commodities and timber and wood fuel products. If we look at this partial dependence plot of canopy opening with distance to markets, we see closer to markets, canopy opening is likely, but there's also this signal further away from markets, which I'll get to in a moment. And then these are some partial dependence plots of roads, and that's just to say that roads are also helping to facilitate this urban demand for agricultural commodities and timber products. So that signal that was further away from markets, we think is caused by fire. So in previous iterations of this talk, I used to say that fire in this landscape was strongly correlated with land cover change, but as we all know, correlation doesn't equal causation. But the second chapter of my PhD uses methods of causal inference to try and identify this causal link with fire and canopy opening. And so what we found is this feedback loop. And I should just mention as well, in savanna systems, fire is a key component of their functioning. So fire is not necessarily incredibly bad here, but we found this feedback loop where fire is a greater effect on canopy opening than canopy opening is on fire. So what we did was we simulated the effect of fire in the landscape by finding the difference between 0% fire in the landscape to 100% fire in the landscape. That increased canopy opening by 61%, whereas changing canopy opening from 0% to 100% increased fire by only 11% throughout the whole landscape. Now, what does this mean? What are the consequences of this? Well, it can lead to runaway change and unintended consequences where fire can potentially amplify itself throughout the landscape. And just linking this back to conflict, another study, Caterino et al. 2020, found that the highest number of burnt areas in Angola were found towards the end of that wartime period in 2002 onwards to about 2005, which they also associate with the resettlement of displaced people. And then, of course, there's potential other interactions with fire and conflict in the woodlands where fighting may cause a more open structure, which is more flammable, allowing fire to burn. There can be potential increase in ignitions from conflict, and then also potentially incentives for combatants to suppress fire so that they can use canopy cover as cover to hide. So to summarize then, we found an increase in canopy opening towards the end of the Civil War associated with the resettlement of displaced people. There's been an increase in urban demand for timber and woodfield products, and there's a sort of ubiquitous use of fire across the landscape, which can cause canopy opening. We found there was this regrowth of canopy closure, this peak in canopy closure a decade later, after the end of the Civil War, which has been sort of facilitated by the remoteness of the landscape due to the conflict and also the resilience of the Miombo ecosystems. So just a bit about the conservation agenda in broad terms. It's an attractive landscape for conservationists because of this remoteness, and there's a number of organizations that are interested in this landscape now, and I guess that's what my work was initially trying to inform. But the conservation agenda in Angola is still recovering from the Civil War, and progress remains slow in promoting conservation there. That's it. Thank you very much.
Thank you, Chris. Any questions? Yeah, Lina.
Yeah.
Thank you so much. This is a very interesting talk, and I was wondering, you mentioned some drivers like of fires, conflict, and the use of fire. But what would you say are the main drivers, and what about the fire season, like the normal or natural fire season?
So the main drivers of the land cover change, the land cover change classes, or drivers
of fire.
The fire. So fire is used in many different livelihoods as a tool in people's livelihoods. So it's used for charcoal production. It's used in apiculture, honey. Honey, I don't think this is working.
It's not working.
Yeah, it's used in collection of honey as well to smoke out the bees. It's used in hunting practices to drive animals. It's used in agriculture to prepare crops. So these are lots of sources of ignition. And in that post-war period, Caterino et al. Found that many people returning to rural areas used fire a lot. And because this is such a remote area with little infrastructure to stop fires spreading, it creates these large burned areas. Yeah.
Thank you. You brought really an interesting point about perspectives from the biodiversity conservation. So what this uniqueness and remoteness creates, but thinking about so-called military forests, can we consider this as kind of a novel sort of the system, of course, human affected, which maybe requires extra attention? The reason why I'm bringing it's with the ongoing conflicts, also bring an example of the Ukraine and past conflict in Bosnia and Herzegovina. These lands are still not fully recovered after the war, and governments, they always want to put so-called military forests, which could be both danger for people who collect some things from the forest, but also for the biodiversity. What would your potential outlook on this type of the areas in terms of the conservation, and maybe some advices from your work? Thank you.
I'm sorry, just to clarify, is that just asking conservation implications because of the war and the military component of that? Is that right? Okay. Yeah, so I guess it's the war has facilitated this remoteness, and there's lots of contamination from landmines, and clearance of that is ongoing. I think one of the key things is the marginalization of communities that live in this landscape and the past associations with UNITA. I think there's still a lot of work to be done to involve government in decision-making processes and involve those communities in higher-level decision-making processes in this landscape, and just to being able to give them a voice in the wider conservation agenda. Yeah, because at the minute it's kind of a bit of a top-down approach, is what I feel like in this region. Yeah.
All right, that concludes our first half session. We do have another one in the afternoon, so I do hope to see you back. So yeah, enjoy your lunch, and I'll see you later.